thermal analysis of biodegradable materials or biopolymers. This is going to be presented by my colleague Samaya. She's just waiting on deck here. I'm going to present a few introduction slides. So my name is Megan Fielding. I work with C-Therm at the products you're going to see on screen today, the Regaku products, as well as the Trident thermal conductivity product. So who are we? We are C-Therm Technologies. Our focus is on simplifying thermal conductivity testing for the materials of tomorrow. We focus on transient thermal conductivity methods. Those are the faster methods with typically smaller sample sizes. You'll see on the right of the screen there our Trident thermal conductivity instrument. There are 3 sensors available on this instrument. I won't be talking much about these today. The main focus is going to be the Regaku products today for thermal analysis, but we will go through a few slides just at the end on the applications in thermal conductivity. So C-Therm is partners with a couple of great groups. First of all, Metrovib, they do great DMA instruments based out of France. And the topic of today would be the Regaku products you see on the right there. So we have the DSC Vesta, we have the STA, which is a combined system of TGA and DTA or DSC, and also the TMA for measuring thermal expansion. Samaya will actually be touching on all 3 of these today on the topic of biopolymers. It's going to be a great webinar. I'm very excited to introduce her here, so I'll keep the introduction quite short. But one thing I do just want to mention in advance is the sample observation technology available on these instruments, on the DSC and the STA. Again, Samaya is going to talk about this and share some examples of this, but I just wanted to give a quick little teaser of the sample observation camera. We see here just an example, a quick example of the STA, simultaneous thermal analysis. So you see the green curve there is the mass loss, TG, and the DTA is the blue curve there, or DSC. So basically with the sample observation system, you can see the sample through the entire ramp. So on the screen here, we see the sample going from about room temperature all the way up to 350. We see it even go through its combustion at the end. So just a quick little teaser, and again, Samaya will touch more on this as we go. So like I mentioned, very short and sweet introduction. The main bulk of this presentation is going to be done by Samaya. Samaya specializes in polymers, so this is right up her alley. She has a PhD in chemical and biotechnological engineering from the University of Sherbrooke and has experience with many different characterizations, mainly including DSC, which again will be a focus of this webinar today. So I think with that, I will stop sharing my screen and invite my colleague Samaya on screen.
Hello, everyone. Thanks, Megan, for your nice introduction. As she said that today we want to focus on the biodegradable thermal analysis of the biodegradable materials. I share my slides and we can start it. Again, good day, everyone, and thank you for joining us today webinar of thermal analysis of the biodegradable polymers. In this webinar, I will focus on the brief introduction of the biodegradable plastics, thermal methods in evaluating properties of the biodegradable materials. Then I will go through some example. First, I start from the sampling method, application on the starch-based fillers by STA, evaluation of the plastic straws made by the PP, PLA, PHBH by STA, DSC, and TMA, and thermal behavior of the biopolymers in direct delivery in STA, by STA and the STA in conjunction with the humidity generator. As all of us now, increasing the waste disposal, marine plastics, pollution, climate changes have become a major issues of these days globally. It has been shown that the global plastic waste production in 2020 was around 367 million tons, and this amount is going to be triplicated by 2060. Therefore, there is a need to develop a new material to replace plastic waste. Biopolymers generally are defined as a polymer formed under natural conditions during the growth cycle of the microorganisms. Due to their abundance, biocompatibility, unique properties, and they are very promising materials in many different applications, such as food packaging, automotive, and cosmetic industry. Thermal analysis of the biodegradable plastics, the International Confederation for Thermal Analysis and Calorimetry defined thermal analysis as a group of techniques in which a property of the sample is monitored against time and temperature, while the temperature of the sample in a specified atmosphere is programmed. Here in this table, you can see that some physical properties of the material that is measured by thermal analysis. But today, I will focus on the STA, simultaneous thermal analysis, DSC, differential scanning calorimetry, and TMA, thermomechanical analysis. Simultaneous thermal analysis is a technique in which a sample temperature is subjected to a programmed temperature change while the samples or reaction product mass change TGA and the heat flow difference DTA or DSC between the sample and reference material is monitored as a function of temperature or time. However, thermogravimetry analysis is a technique where the sample change in a mass is measured continuously during the heating, cooling, or temperature hold. Finally, differential thermal analysis DTA is a method where the sample's endothermic and or exothermic reaction is observed during the heating or cooling scan. Here you can see that example of the STA data. This data comes from the calcium oxalate monohydrate is a standard material for TGA method. In this thermogram, you can see that the TGA and DTA curve, the green curve is related to the TGA analysis and the blue curve is related to the DTA analysis. In TGA, we can see that three mass loss. The first mass loss that is shown to the dehydration or losing of water, which is denoted to the endothermic peak in the DTA analysis. Then we have followed by the second mass loss, which is related to the combustion of the calcium carbonate. Since this experiment is done in the air, we have some evaluating of the carbon monoxide and carbon dioxide as well. And finally, we have the last mass loss, which is related to the decomposition of the calcium carbonate. Differential scanning calorimetry, or DSC, is a technique in which the heat flow rate or thermal power of a sample is monitored against time or temperature, while the temperature of the sample in a specified atmosphere is programmed. DSC is a good technique for the measurement of the temperature and energy changes or enthalpy due to the endothermic or exothermic reaction that occurs as a sample is heated or cooled simultaneously. By principle, DSC is divided in two types, heat flux type or power compensation type. Usually the power compensation type was developed first, but nowadays the heat flux type is widely used all over the world. Here you can see that example of the heat flux type DSC data for the amorphous rich PET. Usually amorphous materials, we can see that the changes in the baseline in the amorphous rich polymers. The first transition is related to or denoted to the glass transition temperature. Then we have the exothermic peak, which is related to the crystallization that is followed by the endothermic peak, which is related to the melting temperature of the amorphous PET. In addition, we can determine the onset and inset temperature and also the enthalpy and energy of the exothermic and endothermic peak. In this example, you can see that the enthalpy of the exothermic and endothermic peak is the same since it is amorphous. The second example I want to talk about is a thermal behavior of the starch-based field by STA, TGDSC. Starch usually consists of the two phases, amylose and amylopectin. Amylose is the amorphous part and amylopectin is a crystalline part. In this example, starch is blended by plasticizers and some fillers, namely nanoclay, cellulose nanocrystal, carbon nanotube. And we use two types of the starch-based filler. One is corn starch-based filler, and the second one is unknown-based starch-based filler. In the thermogram behavior of the corn starch fillers, which is determined by the STA, you can see that the TG and DTA. The TG is a green curve, and the blue curve is denoted to the DTA. Also, we have some sample observation. Unfortunately, due to the limitation of this app, I cannot play it now, but at the end of this webinar, I will play it, and you can see that the first mass loss in the TGA is denoted to the water loss or dehydration. And the second mass loss, you can see that very small endothermic peak in the DTA. Usually people consider this a small endothermic peak as a noise, but it's not a noise, it's a melting of the starch-based filler. Then we have the combustion of the cellulose nanocrystals, and finally we have the exothermic peak, which is related to the combustion of the starch. The unknown starch-based filler, it followed the same trend, both for the TGA and DTA. We have the 4 mass loss in the TGA curve, and also a small endothermic peak at the 162, which is followed by the exothermic peak and at 254, and the wide exothermic peak at 381. Which is related to the combustion of the unknown starch-based filler. In order to have a better idea about thermograms of these two kinds of the starch, we plotted all the curve together. As you can see that the blue curve is denoted to the corn starch-based filler, and the red curve is related to the unknown starch-based filler. In the TGA, you can see that there is you cannot see a lot of changes between two kinds of the samples. But in the DTA, you can see that some small changes you can figure out during the exothermic peak and also endothermic peak, which is related to the difference in the composition and crystalline structure of these two samples. The next example I want to talk about it is a plastic straw made by polypropylene, PLA, polylactic acid, and PHPH, which is polyhydroxybutyrate hydroxyhexonate. Usually plastic straw, which is available in a market, comes from the polypropylene. However, in this example is a really good example to compare it with the biodegradable polymers such as PLA and PHPH. Thermal analysis is figured out with the STA, DSC Vesta, and also TMA. First, we look at the TGA, DTA result of the plastic straw, which is made by the PP, PLA, PHPH. In this example, we used 4 to 5 milligrams of the samples heated from the room temperature to 60 degrees Celsius with the heating rate of the 20 degrees Celsius per minute in an inert atmosphere, nitrogen flow. As you can see that the green curve is related to the PHPH, the blue curve is related to the PLA, and the red curve is related to the PP. The thermal decomposition of the PHPH is much higher than the PLA, and after that, it's followed with the PP. In the DTA, we can see that couple of the transition temperature which is they are all endothermic peak, but we didn't figure out this gonna be related to the melting temperature or other transition. Therefore, we did another experiment. In this thermograms, we observed the changing of the properties of the samples visually. But at the end of this webinar, I will show you how the sample is changed when we heating from the room temperature to 60 degrees Celsius. But Without this observation, we couldn't figure out this small exothermic peak at 149 is related to the melting or other transition, and the big endothermic peak at 306 is related to the decomposition of the pH-pH. Then we figure out the DSC result of the plastic straw made from these three kind of the samples with the first heating scan and the second heating scan. We collected the data from the first heating scan and, as I said, from the second heating scan as well. The green curve again is related to the pH-pH, the blue curve is related to the PLA, and the red curve is related to the PP. The samples was heated from the minus 50 to 100 degrees Celsius with a heating rate of the 10 degrees Celsius per minute and cooling rate of the 5 degrees Celsius, and the amount of the sample was 5 milligram. In the first heating scan in the pH-pH thermogram, we didn't see any transition. However, in the second heating scan, we can see that a small transition at around 60 degrees Celsius, which is related to the glass transition temperature of the pH-pH. This is also interesting for the PLA. We see the glass transition temperature in the first heating scan around 60 degrees Celsius, which is followed by the exothermic peak and then two endothermic peak. However, in the second heating scan, we didn't see this kind of the transition. We just see that the exothermic peak before the main endothermic peak and the last finally endothermic peak, which is related to the phase transition of the PLA and also melting of the PLA. The thermogram of the PP was much more simple. In the first heating scan, we just see that the melting temperature at 160, and in the second heating scan, we saw two endothermic peak, which is related to again to the melting temperature of the PP. Since the thermal analysis of these samples was really interesting for us, the last experiments that we done, it was the thermomechanical analysis of the plastic straw made by the PP, PLA, and pH-pH. The sample thickness was 0.15 millimeter, and the load applied, it was 200 Kelvin, and also the mode was the non-differential one. The sample was heated from the room temperature to 180 degrees Celsius. In the thermogram, in the TMA data, you can see that the softening or shrinkage of the samples of the pH is much simple. We have just one single softening, and then it's melted at around 160 degrees Celsius. For the PP, similarly for the PP, have the same trend, and we have the same shrinkage or softening, and finally it's melted as 170, around 170. And finally for the PP, but for the PLA is much interesting because we can see that three softening or shrinkage in the TMA results of the PLA. The first softening is related to the glass transition temperature of the PLA, which is followed by the second one, and finally we have the melting temperature of the PLA at 160. Again, we put all this data in the same graph in order to have a better idea about the thermal analysis of these plastic straws. As again, you can see that in TMA analysis, we have the three shrinkage or three steps, which is, but we don't see that the cold crystallization temperature in the TMA. This is just observed in the DSC experiments, which is followed with the two endothermic peak, which is again related to some transition in the PLA and finally melting at 164. In detail analysis, it was not, we couldn't observe the glass transition temperature. However, we can see that the cold crystallization temperature and also melting temperature. The last example today that I want to explain is a thermal decomposition behavior of the polyethylene glycol in inert and oxidized atmosphere. Polyethylene glycol is an aliphatic polyester biopolymer used in the biomedical field. The red curve is related to the polyethylene glycol in the airflow, and the blue curve is related to the DTA analysis of this sample in the inert atmosphere. TGA curve shows similar pattern for the both samples. However, in the DTA curve, we can see that the endothermic peak at around 222, then followed by the exothermic peak and two endothermic peak, which is related to the melting of the polyethylene glycol in the airflow. However, in the nitrogen atmosphere, we couldn't see the exothermic peak around 337.3 centigrade, which is related to the oxidation of these samples in the airflow. Here is a list of some instruments that we use in the C-Therm. We have many different instruments for the analysis of the thermal analysis of the polymers, not biopolymers, because today I talked about biopolymers, such as STA, TGA, and DSC, STA in conjunction with the humidity generator, TMA, and also DSC sample observation. And also, we are connected with the Rigaco instruments as well, such as standard thermal analysis and also hyphenated techniques, thermal analysis that we can use this kind of technique. They are super interesting because at the same time, we can determine the thermal analysis, for example, with the mass spectrophotometer or FTIR analysis, and gives a very good data in order to figure out what kind of samples we have and what kind of condition we can use for our materials. That's all for me. Thank you very much for your attention. I just shared a video and play some video that I was talking about it, and then I will give this talk to my colleague to, and you, if you have any questions, you can ask me. First, let's ask to I share some of my videos that I talked about it. You can see that in this video, as we can ramp it up the temperature, you can see that the melting temperature at 149 degrees Celsius, that is followed with the composition of the starch-based material in the DTA and TGA and sample observation is really, it gives a very nice and precise analysis with this observation, and it's going to be so useful in determination of the properties of the samples. Thank you very much.
Thank you very much, Samaya, for that presentation. I'm just going to bring up a few more slides here at the end. So as I mentioned, we are just going to go over a few brief slides on the thermal conductivity side of things. When you're doing thermal analysis, it's really important to have kind of a full picture of your sample, and that includes, the DSC, the STA, the TMA, but it also includes thermal conductivity. So as I mentioned here at C-Therm, that is what we focus on, the thermal conductivity side of things. So let's go through a little bit of background here. If you're new to thermal conductivity, I'm not going to spend much time on it, but just to give a very quick introduction, thermal conductivity basically describes a material's ability to conduct heat. It's measured in units of watts per meter Kelvin. You can see that on screen here, how we get those units. You may be familiar with this property. So materials like metals are very high conductivity, whereas materials like polymers or insulations are very low thermal conductivity. So specifically to polymers and biomaterials, we'll take a look here at how heat transfers within a polymer. So there are a few things you can relate to the thermal performance here. We see the equation on screen. K is the thermal conductivity. So this K value can be related to the volumetric heat capacity, which is denoted by uppercase C. Also the speed of sound or in the material, which is V, and the mean free path of photons, which is L. So we'll focus here a little bit on the mean free path as we go along in these few slides here. So when we're looking to quantify the overall performance of a polymer, you can take a look at the sample structure. For example, on the screen here, we see samples that are amorphous, we see samples that are crystalline, and this has a very large impact on the thermal conductivity. As you can see on the screen there with the arrows, as you decrease the mean free path or alternatively increase the organization, the thermal conductivity will actually increase. So this basically describes why a crystalline polymer or a very organized polymer will have a higher thermal conductivity value or K value as seen on screen in the equation there than an unorganized polymer. Typically, unorganized polymers are not quite as efficient in heat transfer or thermal conductivity. So you may be wondering, how do you increase the thermal performance or increase the thermal conductivity of a polymer? So there are a few ways. The first, as we've talked about in the last couple slides, would be to improve the organization. As we just talked about, a more crystalline structure equals a higher thermal conductivity. Another way that a lot of groups we work with are attempting to raise the thermal conductivity, they're adding a conductive filler. So a higher load of the conductive filler will, of course, result in a higher thermal conductivity. But that's not the only thing to consider when adding a filler. You also need to consider the orientation of the filler. The aspect ratio of the filler will have an effect on the thermal conductivity, and there's been quite a lot of work done in this field. If you're interested in learning more about this, we have many application papers on this. But I'll go through maybe one quick example on a group that was looking to increase the thermal conductivity of their polymers. So this work is out of the University of Akron in the US, the Chemical and Biomolecular Engineering Department. So let's take a quick look at their study entitled Regulating Intermolecular Chain Interaction of Biopolymer with Natural Polyol for Flexible, Optically Transparent, and Thermally Conductive Hybrids. Okay, so I'm not going to go into too much detail. Again, if you would like to learn more about this paper, it's available on our website, along with many others doing similar work. But I'll give a brief explanation of it. So they took their SCMC sample. They actually added some xylitol into the sample to increase the mean free path. And by doing that, we see here on screen that they actually were able to optimize the thermal conductivity. What they did to test this sample was they used the modified transient plane source method, MTPS. This tests according to ASTM D7984. And you'll see that picture on the right of the screen there. That's the MTPS sensor. And just that's a picture of a person placing the sample on top of the sensor. As you can see, it requires a very small sample. It's quite the easy setup. You basically just place the sample on the sensor, you'll place a weight on top, and that's about it. So quite an easy method, very fast, very repeatable between users. We see a lot of groups prefer this method, especially the academic groups where they may have many students coming through the lab and need a very quick, easy method to test thermal conductivity. So the MTPS is quite popular for studies such as this. And just a couple of quick conclusions. As I mentioned, I don't want to go into too much detail as we've done a lot of work in this in the past and have many webinars and papers available if you'd like to take a deeper look at this. But just to conclude, thermal conductivity is a very important performance metric for biopolymers and thermal applications, in addition to the other thermal analysis instruments we talked about earlier, the DSC, STA, and TMA. One way to increase the thermal conductivity is decreasing the mean free path, or in other words, increasing the organization of the polymer. And finally, the transient methods like the MTPS method are a very efficient way of measuring the thermal conductivity of the biopolymers. So that's going to be it for thermal conductivity here, and I will just share the final outro slides as we approach the Q&A here. Okay. So I mentioned that we have many additional resources available. You can see on screen here how you can get to those. So we've done many webinars in the past on both Regaku and, of course, on our thermal analysis. Many different specific subjects, polymers, EVs, batteries, insulation, basically whatever you can think of. We probably have it in our webinar library or our tech library. Both great resources if you're looking to learn more. Alternatively, please feel free to ask questions in the chat and we can definitely point you in the right direction for what you're looking for. And we do have a few upcoming events we would love to see you at. I myself will actually be headed to the Advanced Materials Show next week in Pittsburgh, Pennsylvania, and have some colleagues headed to France October 24th to 28th for a show there. So hope to see you there. If you're going to be there, please let us know. We'd love to say hi. And we do have a few upcoming webinars I'll let you know about. We have conductive fillers in polymer composites coming up on Thursday, October 20th. That will be a very good one. I'm sure the folks watching today will also be interested in that similar topic, but just more in detail about the thermal conductivity side. We also have another webinar coming up for EV kind of applications, high performance potting compounds. That's in November. So hope to see you at some future webinars as well. And another way to get some great info is following us on LinkedIn. We like to post there upcoming webinars, upcoming events. If you'd like to stay tuned for those and blog posts, etc., please give us a follow on LinkedIn and it will be up to date on all the things we have coming. Now, if anything today was interesting for you, you'd like to learn more, perhaps you'd like a quote for either end of year budget or maybe budgeting for next year, please feel free to reach out. If you leave a comment in the chat about what you're interested in, we'll make sure the correct person gets back to you and answers your questions and helps you out. And with that, we have made it to the Q&A. So I'll leave this slide on screen. It has both my info and also Samaya's info. And I'll invite Samaya back on the screen here and we will take a few questions. Okay. I'll look through the chat here, excuse me, and pull out some questions. We'll probably have time for 5 or 6 here. Okay. So the first question here, Samaya, I'll let you answer. What temperatures is the DSC camera available for and for the STA?
For the DSC, it usually goes from -70 to 350 degrees Celsius, and for the STA from the room temperature to 1000 degrees Celsius.
Perfect. Another question I see here is also related to the DSC. I've heard modulated DSC is the best type to use. Does your system have modulated DSC?
Yes, it is. I agree with that. I recommended the modulated DSC of the Regaku because it's really easy to differentiate between irreversible and reversible reactions, and you can easily differentiate the reaction from each other. And I say that I really recommended it. It's really nice to determine the heat capacity and enthalpy from the modulated DSC.
Yes, great way to determine heat capacity. If you're looking to measure heat capacity, we would definitely recommend the modulated.
It is.
Okay, another question here. Sometimes I can't get clear results in my DSC. Should I change the parameters?
Clear result from the DSC? It can be, it really depends because sample preparation is really important for the DSC, the amount of the sample that we use and what kind of the crucible, and also the parameter of the DSC. I cannot say generally it doesn't have the simple answer. It's really, it depends of the parameter of DSC, the DSC machine, and also how the sample preparation going on. Sometimes we use some kind of the composite. It's not an easy composite, and we can see that some weird data in the DSC analysis.
Yes, and we would be happy to help if you'd like to share
Yeah,
some more
exactly.
details.
Yeah,
We'd be happy to follow up there.
yeah, me too. I will be happy if I can follow in more.
See, I think there were a couple more above. Okay, I need to test my samples under argon. Is that possible with the DSC and STA?
Yeah, it is. Our DSC can be, it's equipped with the inner gas, argon and nitrogen, and also we can use it in the air, and we can switch it between the different atmosphere as well, from the inert gas to the air as well. In our last webinar, you can see the good results that we did it from the rubbers, and we switched the nitrogen to the air atmosphere in order to determine the amount of the carbon in the DSC from the DSC data.
Yes,
We
as Samaya
refer you.
just
Yeah,
mentioned, yeah, there was a great application in our last rubber webinar. So
yeah,
if you're,
exactly. We can. Yeah, I refer you to go and see our labs webinars.
yes.
Thank you, Megan.
And I think one last question we'll take here today. I have limited space. Can the samples or the instruments be controlled with one PC?
Sorry, can you repeat it again?
Basically, can the all three instruments be controlled with one computer?
It's possible with the one computer as well. You can connect it to the all instrument in the one computer with the same software and observe the data simultaneously together. It is possible, yeah.
Yes, absolutely. It's a great space saver. You don't have to have a
Yeah, it
separate
is.
PC for each instrument. They're
Exactly.
all run on the same computer, run on the same software, and all three can be run simultaneously. So
It
yes,
is.
that's no problem, and it's a great space saver for sure. Okay, I think that will be good for the questions today. If we missed your question, we will absolutely follow up by email. And if you have any follow up questions, our emails are there on screen. Please feel free to reach out. We're more than happy to chat. If you'd like a budgetary quote, happy to help with that as well. So I think we'll wrap it up for today. Thank you so much, everyone, for your time and for attending this webinar. We really appreciate it, and we hope to see you on the next one or at one of our shows we'll be at in the coming months. Thanks, everyone. Have a great